rate of reaction. Bit of a filming gap, you can tell by the hair. Comparative initial rate analysis. Very common question at A level. Examples like asking them fairly straightforward questions to set up. Very easy to analyse, very easy to set multiple choice questions on, set slightly longer answers on. Therefore, very popular type of question because of the variety of questions you can ask. It doesn't involve any graphs. The truth is, it does involve graphs, but they've been done for you. So it comes off of initial rates. So when you look at this, you'll have this, and this is a slight curve, so you'll have a tangent for the initial rate, and you'll get the gradient of the tangent. But all of that is done for you in these comparative rate questions. And they're always the initial rate, so it's comparative initial rate is the title. So you're going to need to make some notes as we go along. You're going to need to pause me when I put a set of data on the whiteboard, note that down, and then restart it so you can go through the analysis with me. So it's going to be a bit of a stop-start video for you, always stop-start for me. So that's the basic idea. Some numbers in a table. The hard work in terms of plotting the graphs has been done for you, and you'll see a lot of these at A level. I'm going to put the example one on the board because the best way to get into these is to just get into an example, and I'll see you when I'm ready. So here we are with the first example. At this point you need to pause me and get this table of data down. So now you've got that down, we're ready to analyse it. When you look at these questions, you will see there will be runs, they might call them experiments, and they'll be either numbered or lettered probably. And you have an initial concentration of chemicals. So this is a reaction where A and B are being, well, there must be the questions. Now what I'm doing is I'm not focusing on actual chemicals, I'm just doing letters to represent general chemicals. So we've got non-specific chemical A, non-specific chemical B. That has no relation to this. This just happens to be A, B and C down the side instead of 1, 2 and 3. And we have an idea of relative rate. Now relative rate takes away the need to think about the units. So there are no units for rate. This just tells you that the first run had a relative rate of 1 and this one was twice as quick. Doesn't actually matter. The numbers could be 0.006 and 0.00. 0.006, 0.012, that's better. So, but I'm getting around that by having a relative rate where this was given the value 1 and these were multiples of what the rate was at this point. Now, how do you do it? Well, you look at the whole set of data, because somewhere in the set of data, no matter how complicated it is, there will be a pair of experimental runs where only one concentration is different. Now this is about as basic as it gets because it's very straightforward, but we've got to do that to get our heads in the idea of how we do this. We'll make it more difficult as we go into other examples. So when you look at runs A and B, this is the same, it's only this one here that's changed. And you look at how many times one is of the other. In this case this one's twice that one. So in my analysis, which is being done down here, concentration of A doubled. Now when you go doubling of the initial concentration, this one hasn't changed, the rate, because it's relative, has also doubled. So, when you do that, if the rate doubles when the concentration doubles, that's a straightforward proportional relationship. That is first order. You might need to pause me at this point and catch up. Then we go on to analyse runs B and C. Now why do we choose B and C? Because now A stays the same, but the concentration of B is now doubled for the initial setup of the experiment. And here, when you double the rate doesn't change. So when the rate doesn't change, so the rate is not affected by the concentration, that is zero order. So we have first order with respect to A, zero order with respect to B, and assuming there are no other chemicals, because I don't want it any more complicated than two chemicals, that means that is the rate equation. B is to the power of 0 and disappears out of the rate expression. And so by looking at pairs of runs. Now, why didn't I pick A and C as a pair? Because both of those have changed, and therefore you can't tell which one is responsible for the doubling of the rate. So you have to select the right pairs in order to do the comparison of concentration against a comparison of rate. That's a very straightforward example. If you're not sure what I've done, rewind it and replay the explanation. And if you're all good with that, we'll move on to example 2, which of course I need to get on the board. I'll see you in a moment. So here we are with example 2. Example 2, a little bit more complicated, as is the way with these things, we develop your understanding. So you're going to need to write down the setup data, and you're going to need to pause me in order to do that. So you're going to need to pause. Okay, you've done that. So here's a set of data, not the same as setup even as last time. We've actually got a real rate this time in moles per cubic decimeter seconds to the -1. Although my 3 is pretty poor quality. But there we are. Right, so we actually have now the ability to go on down here to do something else. But we'll come to that. Don't look down there. We'll come to that a little later. We need to do the analysis first. So, not even a doubling this time. So you need to look, okay, what can we do? Well, we can look at that pair, because that pair has this the same and that's changed. And then this pair, they're the same. And there's the change for C and D, because these are now C and D. C is this, A is this pair, D is the lower pair. So when you look at comparing runs A and B, the concentration of C has gone up times 10. You can see that. The rate has also times 10. It's first order. Now, when you look at B and C, where the concentration of C has not changed, chemical C that is, so here, this is now 4 times bigger. 4 times 0.5 is 2. The rate has gone up. How many times has the rate gone up? Well, you take one and divide it by the other. So 0.8 divided by 0.05, and the answer is 16 times. So times 16. So that's not a first order relationship. Now, of course, the wise among you will have noticed that 4 squared is 16. And it's second order. So that means our rate equation for this example will be C to the power of 1, D squared, or D to the order of 2. Now, when you've got an actual rate rather than a relative rate, you can work out the proper value for the rate constant. So knowing the rate equation, because you cannot work out K until you've got a rate equation, you then pick any row, because it doesn't actually matter which row you pick. Each row should give you the same answer, or very nearly the same answer if it's real data. These are constructed data, so they come out perfectly. So you substitute in the numbers. I've used the last row here for my calculation. So my rate is 0.8. It's rate constant times concentration of C, which is 1, and then the concentration of D squared, which is 2. So that makes it, when you rearrange it, and the 1 disappears, and you get left with K, it's 0.8 divided by 4, which means K has a value of 0.20. And then if you think back to a couple of videos ago, we were working the units out, so it's dm to the 6 moles to the minus 2. Ooh, I've written moles to the minus 1. Dm to the 6 moles to the minus 2 seconds to the minus 1. If you don't know how to work out the units of rate constant, go back to the couple of videos before and have a look at that. If you're not able to work out rate constant units, you're kind of not ready to do all of this. You need to go back a bit in the topic. So then we have a slightly more complex example. Overall, this is third order kinetics, not something you see that often, but it's just serving to make a point. It does tend to be more complicated when you get this initial rate comparison type analysis, because that way you can introduce higher levels of complexity in the rate equation without making the question too overbearing. Right, we're going to do another example, but of course I need to get the board ready. I'll see you in a moment. So here we are for example 3. Now I've called example 3 deductive reasoning. I'm sure there are lots of other names for it, but in example 3 we get the more complex type of analysis that you quite often see in A-level questions. So yet again, you're going to need the set of data written down. So you're going to need to pause me and write the data down, and pause me. Okay, you've written the data down. So the analysis, where do you go? Now the data, when you look at it, is much more, it's confusing for a number, well, more confusing, more complex, because firstly there were 3 chemicals to consider. Secondly, when you look, it's quite hard to see a pair for each, well, there isn't a pair, you can't find a pair for each of the chemicals E, F and G. So where do you go? Well, there is always going to have to be a pair of runs, and it doesn't have to be the first 2. I mean, it can be somewhere else in the setup. I mean, you know, it depends how annoyingly awkward the exam board wish to be. But I've got it on the first pair where only one concentration changes. So here, this concentration changes and these are the same. So therefore, that makes runs A and B able to determine the effect of the concentration of E changing. Now I've also not put the units of concentration in just to make it not so cluttered, but obviously it does have the units of moles per cubic decimeter. So when you look at runs A and B, the concentration of E, yeah, I wrote the wrong thing down. Concentration of E has doubled. The rate has also doubled. This is a relative rate question, so we can't do the rate constant at the end. So that's doubled, that's first order. Quick as that, done. Now, runs B and C. That's where it gets a little more complicated. Because when you look at B and C, both of these have changed and this one has stayed the same. That's quite important because it allows you, with this one staying the same, to know that that one's not getting involved in any of your thought processes. But you quite often get a question where now, once you get past the first pair of runs where it allows you to pick whichever chemical it is, E in the case of this question, find out its first order in this case, you then use this information in your determination of what's going on in these runs. So when you look at runs B to C, I've written a couple of things down there to guide you into it. We have to include this thought process of, oh, it's first order with respect to E when we're thinking. Now the rate has doubled, 2 to 4. Okay, so we've got to account for a doubling of the rate by the data. Now we already know that E is first order. Now when you go from there to there, E has doubled in concentration. So if E doubles in concentration and it's first order, it will double the rate. And that's all we need. Although my cat has decided to join in. And joy. He doesn't understand chemistry, that cat. He's just making a fuss. because he wants food. So the concentration of E is doubled, and that accounts for all of our rate change. So F, even though F is doubled, we already know that that doubling has come from there. There's nothing else to consider, because all of the change in rate we can attribute to the concentration of E doubling. Doubling the E, first order, doubling the rate. F doesn't have any effect, therefore it's zero order. Now you're going to need to possibly even rewind me and have another go through that. And then I haven't got enough space to do C and D, so I'm going to clear the space out for the analysis of C and D, and I'll see you in just a moment. So final analysis, I'm using run C and D. Now you don't have to use run C and D. You could have used A and D, it doesn't matter. You just have to put the right numbers in and think about it right. But I've picked C and D because it keeps the numbers a little bit easier to manage. But you can genuinely pick any pair to do this kind of deductive analysis once you've cracked the first one. So when you look at C to D, all three chemicals are changing in concentration. So that your initial thought would be, why would you pick that? But the answer is that you have to deduce this. So, first of all, the rate has increased from 4 to 48. How many times is that? Well, you do the division. 48, big one divided by the small one, it's 12 times bigger. So 12 times the rate. So you've got to account for a 12 times increase in the rate by the changes in concentration and the orders with which they have. Now, concentration of E has gone up by 3. 0.1 to 0.3 is 3 times bigger. Concentration of that with the trebling means it trebles the rate, because we already know E is first order. So 3 times of your increase in rate is accounted for by the change in concentration of E. 12 divided by 3 means we've still got 4 times 4, a quadrupling of the rate to account for. So E3, take that out of the 12, not by subtraction but by division, and we still know we've got 4 times the rate to account for. So that means, what do we do? It's either going to be F or G, but we've already done the analysis for F. F is zero order, so we can ignore it. Doesn't have any effect on the rate, and therefore G must be responsible. Now here G has doubled, but the rate has gone up by 4. That's a second order relationship, that's a squared relationship. So G times 2, second order because it's times 4. And that means our rate equation, K, concentration of E, concentration of G squared. End of question. Now I think if you're not familiar with that, or you're feeling a little bit unsure about that, I would run it back and watch the whole thing again. You're going to need to make your notes crystal clear. And then we've got a even more irritating example, number 4, to do before the end of the video. But obviously I need to get the board ready, and I'll see you in a moment. Okay, so last example, more complex deductive reasoning I would call this if I gave it a title. So 3 chemicals yet again, so that means 4 runs. Oh, complicated when you look at it. You look at that, you go, oh, I don't know, I should put a line down there. Let's put a line down there. So you look at A and B, and the concentration of everything has changed. It's not runs A and B. So the first thing you've got to do is search out the way in to solving the problem. And you need to find a pair of runs where only one concentration has changed. And if you look at B and C, that's the same, that's the same. So the concentration of K is your way in. Concentration of K, but even then the numbers are not straightforward. Look. So what's the concentration of K changed by? 0.504 has come, as the higher concentration has come from 0.180. So you divide one by the other and it's 2.80. So the concentration when you go from B to C is 2.80 times bigger. You do the same with the rate, 17.78 divided by 6.35. These are actual rates. Now you'll see it says 10 to the 4 rate. We'll come to that when it actually comes into play, because at the point when you're doing the analysis, the 10 to the 4 is irrelevant. It's only there to mean that these numbers don't have a standard form next to them, which means the numbers are easy, because when you're doing the analysis, you're just comparing the rates, so it doesn't matter about the standard form part, because it's going to be the same on each one. And you do the 17.78 divided by 6.35, 2.8 again, both the same 1:1 ratio, however you want to word it. It's first order. So K, first order. What next? Well, let me get the board ready and I'll show you. Okay, now we have to pick up what can we do next. So we've established that K is first order, but every single row has a different concentration of K. K is not potassium, it's just a letter. So what do we do? Well, we're going to have to use deductive analysis again. But if we look here, L isn't changing in concentration here. Now, we can't do that because we've already done B and C, that was when we did K. So here, L is not having an effect because it's not changing. So that means we now have these two changing, but we know what K is going to do because we know K is first order. So we run through this analysis here. So the rate change, 2667 divided by 17.78 is 150. So the rate has increased by 150 between C and D. Now K has changed by 3.024 divided by 0.504, because that's the two values in there. And that is a 6 times increase in the concentration of K. And because it's first order, that means it will do 6 times the rate by doing from there to there. The rate will go up by 6. Now that hasn't gone up by 6. We know it's gone up by 150. So, but times 6 of the times 150 is coming from K. So you do 150 divided by the 6, that leaves you with 25. So we've still got a times 25 increase in the rate of reaction to account for by looking at what J does. Because L isn't changing, we've dealt with K, we've just got J to account for the 25. So you look at what's the concentration change between run C and D, and you do that there, 0.0450 divided by 9 times 10 to the minus 3, it is times 5. Now times 5 and a times 25 change to account for is a squared relationship. It's second order with respect to J. And there we are. And that just leaves us, what are we going to do to pick up L? Well, I need some more board space to do that, so you're going to have to wait until I've got the board ready. See you in a moment. Okay, last bit is to unpick what's going on with L. Now you could pick A and any other run. I've picked A and B. You could do the same analysis with A and C or A and D, but I've gone with A and B. Now, it's got two pieces of deductive evidence in it. So firstly, you need to find out what the rate change is. Now also, going from B to A is a reduction in rate, or going from A to B is an increase in rate. It doesn't matter which way you look at it. I'm going from B to A because, I don't know, it's just the way I've done it. So 6.35 divided by 0.0147 is 432 times the change. So it's quite a big change in rate. We've got to account for that by changes in the concentration of K, J, take those out, and what's left must be done by L. So, K, 3 times the change in concentration. We know K is first order, so 432 divided by 3 leaves you with 144. Still got 144 to account for, so 3 times change in the rate is accounted for with the first order reaction kinetics of K. Now when we talk about J has reduced in concentration by 3 times. I'm going from B to A, you could go from A to B and say so 3 times that way, but it's a third. But it doesn't matter which way you look at it. That's why I said a third in brackets there. And we know that J has second order reaction kinetics. So J, a 3 times change in the concentration of J will do a 9 times, 3 squared times, 9 times change on the rate. So 9 of the 144. So 9 divided into the 144 leaves you with 16. 16 is always a number you go, oh, I think I might be heading for second order kinetics because you know it's a squared number. And then when you look at the change in concentration of L, it's 4 times. 4 to 16 is a squared relationship. It's a second order reaction. So therefore we have K is first order, J is second order, L is second order, that's fifth order overall. That's horrendously complicated. But we can deduce it from just that little set of data. Now the last thing I want to do is calculate the rate constant. I'm going to need a little bit more board, as you might imagine. I'll be stopping in a second and wiping the board. And also I'll be putting the actual rate equation up. You might like to stop me and write the rate equation out ready for the last little bit of this video. I'll see you in a moment. So hopefully that's the rate equation that you thought about or wrote down. If you paused me, I bet you didn't. Now the last thing, because we've got actual rates up here, the value of K, but it's what to do with the 10 to the 4 when you're doing this. Because this is here to make these numbers more manageable, more in your head. So really, that isn't 17.78, it's 17.78, and that is 10 to the 4 times the value, so it's 17.78 times 10 to the minus 4. So that will be 0.0147 times 10 to the minus 4, because it's the minus integer indices value on that. Now you can do this with any of the rows, because these are constructed data and they all come out the same. And I've picked row C for the reasons of nothing. I've just done it. And so the rate is 17.78 times 10 to the minus 4, which is what I've just said. And then it's K. There's the concentration of J, and we know J is second order. There's the concentration of K. There's the concentration of L, second order, so it's squared. Now, I've combined all of those and rearranged the equation. So I've subbed in the values and then I've rearranged, I've combined all these, and it's 1.045 times 10 to the minus 6. And divided it into, so I brought that underneath there and left K on its own. And it comes out as 1701. But that's not correct in terms of significant figures, because all of this data is restricted to the worst data is 3 significant figures. So therefore it's 1700, because it's not 4 significant figures, even though that is 4 significant figures there and there. But most of them are 3, so therefore the answer has to be 3, because that's the lowest significant figures. The units, if you want to go through the unit analysis, go back and look at the other video. dm to the 12, moles to the minus 4, seconds to the minus 1. All rate constant have seconds to the minus 1 in, as I said in an earlier video, and that's to 3 significant figures. Now, there is a worst case scenario with these, which is not example 5, I'm pleased to say, because we've gone on for long enough with this. And that is where, when you compare a run, one of the concentrations goes up, the other goes down, and you have to deductively include one going up, one going down, and what that does to the rate. That's really got to really think carefully about that. But I'm not sure we're ready for that at this early stage of doing deductive analysis. So there are some attached problems to test yourself on, which is what you need to do. You will then become more competent at manipulating the numbers and looking at how to do this. But that still leaves the question hanging of what is the rate equation telling you? So that rate equation there is telling you something really fundamental about the reaction. today's not the day for that. That's the next video, which is coming up soon. Thanks for watching, and I'll see you when we're talking about what rate equations really mean. Bye bye.